In the previous class, we have studied the Gaussian or normal distribution and how to derive it from the Brownian distribution. That means n is very large and np is quite large, and we assume that p is not very close to 0 or 1. In that limit, it becomes a Gaussian or normal distribution. It is a bell-shaped function. It is a very famous distribution function. And in this class, we just give some properties of a continuous distribution function, or probability density function rather. Some properties, give some properties, and we want to calculate the mean and variance of a Gaussian distribution. This is the agenda of this class, or we will calculate in a first we first we calculate, give some properties, or discuss some properties of Gaussian distribution. Then we calculate the mean and variance of Gaussian distribution. Suppose for a continuous random distribution, random variable, random variable means it always the value of this always depends on chance. That means we always speak of probability for a continuous thing case. We always speak of probability density function (PDF). And suppose that the sample space of a random variable x is from -infinity to +infinity, and px is its probability density function. Then px dx, what does it mean? Just basically mean probability that the random variable x can have in the range x to x plus dx. What is the probability of getting the value x to x plus dx? Px dx it gives you. You just remember from the Maxwell's speed distribution. As this lecture is aimed for physics honor students, that's why I'm just citing this example mostly. And the FVdV or FCDC is the most popular way of declaring the Maxwell speed distribution. FCDC gives you the probability of getting a molecule having velocity c to c plus dc or v to v plus dv. You will get the probability. And probability distribution function px dx, the probability is always greater than 0, and the px dx. And there is another condition, the probability density function PDF, and integrate over the whole space, the space of sample space, that is -infinity to +infinity, integration dx px must be 1. This is popularly known as a normalization condition. It is obvious, these three properties are very much obvious and very standard one. And there is another quantity which is very much important sometimes, that is called the cumulative distribution function, CDF. It is the total probability that the random variable x is less than or equal to any given value x, and it is supposed to be denoted by capital Fx. That means the probability of getting the random variable x, capital X, random variable, some less than or equal to some value x. That means we have to integrate the probability density function from -infinity to that specified value x, and I have used the time variable x prime and d prime, integrate it over, and it becomes the function of x. And fx is non-decreasing because a non-negative function of x that satisfies at f -infinity it must be 0, and f +infinity should be 1, because -infinity means it covers no area under the curve, and that means almost 0 probability, almost 0. And it when x becomes infinity, that means it is a basically -infinity to +infinity integration normalization condition gives you the value 1. It is obvious from the basic idea of calculus, df del f del x, df dx is px, which is basically the probability density function PDF. CDF for Gaussian distribution can be written as capital Fx 1/√2 pi sigma square 1/root square root of 2 pi sigma square -infinity to x, and some time variable x prime minus x average square minus 2 sigma square and dx prime. And from here, and we know SND, standard normal distribution function, fx equals to 1/√2 pi e to the power minus x square by 2, and this is a standard normal distribution, and corresponding the cumulative distribution function CDF becomes some notation fz, some variable fz or z, 1 over root 2 pi minus infinity to z and e to the power minus u square by 2 du, basically up to z, the value of getting the probability is z. And if we distributed it minus infinity to 0, this gives you the value half, and rest of the thing minus infinity to 0, that means half of the distribution is basically half, gives you the value half, and rest of thing 1 over root 2 pi and gives minus infinity to z. This is you have to calculate, you have to integrate it out, and this is basically famous, you know, the error function ERFZ. There are some connection with error analysis in and physical science and engineering, and ERFZ 1 over root 2 pi 0 to z some z e to the power minus u square by 2 du. It is an extensively tabulated. You will get the chart of this function for different values of g. You will get a chart. Any mathematical books, any mathematical physics or mathematics or statistics books, at the end of the books you will get the values. You will get different tabulated values here. This is a very standard tabulated. In terms of it is a very standard function, and pre-computer in a pre-computer age they have calculated this rather in a very painstaking method of numerical analysis and put, and you will get that value. And in this age of computation, you will easily calculate this value in your Python or any standard language, any standard modern languages, in very easy manner by using some algorithms. And well, fz can be written as half, in terms of error function, half 1 plus ERF z by root 2, z by root 2, and this thing. And it is the graph of the density function, sometimes called the standard normal curve, and it is become something like it will not touch, it is asymptotically merges to minus infinity or plus infinity, and from this is standard normal because it is minus 1 to plus 1, the variance is 1 plus minus 1, that means this is plus 1 and this is minus 1. If you calculate minus 1 to plus 1, that is 1 sigma limit, it is basically covered 68.27% area. And if it goes from minus 2 to plus 2, that is 2 sigma, it basically 95.45%. And if you go from mean value in the both direction 3 sigma limit, it covered basically 99.73%. That means the probability of getting any value minus 1 to plus 1, that is basically this, and minus 2 to plus 2 basically 90.9545, and minus 3 to plus 3 is 0.9973. And this is the it covers almost everything, 3 sigma limit. And determine in this context I am giving you a problem, determine the full width at half maxima of a Gaussian distribution. You calculate the full width, full waist of the Gaussian distribution function at the half of the maximum value. This is your home task, and answer is this. Now we turn to how to calculate mean and variance of Gaussian distribution, or PDF. From the PDF, how to calculate the Gaussian distribution. And our recipe is very well known to you. How to calculate in this case is a continuous distribution, and px dx gives the probability of getting the value, the random variable x to x plus dx. That means probability distribution times x, and integrate over minus infinity to plus infinity. And you just put x times the distribution function here. It is well known to you, as we have derived in the previous class from binomial distribution in the limiting condition. And you just put this thing, and after some manipulation you putting this. I am not explaining the every line, and it is video recorded, and you just pause it or slow it, and or rather you try to calculate. I am just giving the putting this variable in terms of t and standard substitution method, and you just giving some simplifications, and after that, after doing this, and it becomes an odd function, it gives you the 0 value, and here only these things, and I am going to the result. I'm just skipping this part, rather I am just slowly shifting the screen, and you just check those who are not familiar with this kind of integration, and I hope you already know how to calculate this. And here you use the gamma function, and after that x average will be in this Gaussian distribution will be x bar, which I have used in our distribution function. And this is a very famous result. X average is nothing but x bar. How to calculate the variance of px from the random or continuous random variable x square average in the similar fashion x square px dx, as we have seen from the discrete case, that is x px, as you have remember, and you just sum it up here, it becomes an integration, and px dx gives the probability, and x is the random variable, continuous random variable. And sigma square in the similar fashion can be written as the square average of the square minus average of the squared quantity minus square of the average, and you take the root, then you will get the standard deviation. Here we give the variance, that means variance sigma square, variance or sd square, that is basically we have to calculate this term. And we know x px is x average, we already know, and x square px dx, that is basically this quantity. And now in the similar fashion we substitute this variable, and after getting that, and we will get this quantity, and this is an odd function, that's why it goes to 0. You just pause the video and try to follow every step I have worked it out. And this is basically the integration I1, and this is basically I2, and I1 is already root 2 pi, and I2 is basically even function, so that's why it becomes 0 to infinity. And putting this substitution, and it becomes, after using gamma function, this is root 2 pi, and if you follow this, it will be x average square minus sigma square. And what is variance? Basically x square average minus x average square, and it is basically x average square minus plus sigma square minus x average square, and it cancels out, and variance is sigma square, that is sigma x, in this case sigma. And so therefore, and we can say for a Gaussian distribution function px, Gaussian distribution function px, which is 1 over root 2 pi sigma e to the power minus x average square by 2, and we have used this kind of thing here. We have used, what is that, basically 2 sigma square, and in this notation not sigma x, sigma square. And this is basically distribution function. In this case the parameter is the 2 parameter, one is the x average, another is sigma. These are the 2 parameters of this distribution function. Well, this is the end of this class.